All right, hi. So welcome to the Eng Mechanics Crash Course. So here's the schedule that we've got today. And if you want to look at my notes, there's a QR code right there. That'll bring you to like a Google Drive with my notes. So I'll be populating that throughout the term. There are some old notes on there from when I formerly taught this. But I'm basically one of the Eng Mechanics demonstrators. I've got 3 classes. I've got one later today and then 2 tomorrow. Since most of you guys are probably in first year, you probably don't know me. So I feel the need to introduce myself a little bit. So I actually graduated from UNSW already in civil engineering. So that was 2 years ago. I worked as a structural engineer for a year last year. And this year I'm starting my PhD. But part of the reason for me why I came back to UNSW is I really like teaching. So hopefully that comes across. And not only do I like teaching, I like structural engineering quite a bit. And so structural engineering is basically a part of civil engineering. And yeah, it's my favorite part of it. And I hope that comes across in this workshop, essentially. All right, so the schedule is we're going to do a bit of yapping. So I'll give you a bit of theory of what this course is all about. More specifically, I'll be talking about the first half of the course, which is to do with statics. And I've got some games for you, basically. So there'll be, I'll explain them later, but we've got some little games. I'll try to make this a bit more of like an interactive workshop so that you guys aren't like bored to death with me just like talking at you. And yeah, so anyway, that's what we're going to do today. All right, so the first thing I want to do is introduce you to the course structure. So in Eng Mechanics, right, ENGG1300, we've got 2 halves. We've got the statics half and the dynamics half. Okay, so I'll explain on the next slide what Newton's laws are, essentially, and where these stem from. So the first half of the course is based on Newton's first law, which is, it's a law of equilibrium, but you can summarize it with the sum of the forces is equal to 0. And then the second half of the course, dynamics, is based on Newton's second law. So that's sum of the forces equal to m times a. It's like a proportionality. So within the first half of the course, we've got the basics. So we're going to go through what forces are, what moments are, and then we're going to go through structures. And there's different types of structures we cover in this course. These are like your fundamental, like basic types of structures. So you've got beams, trusses, and frames. And we'll be talking about those. And then there's a bunch of miscellaneous stuff which will be covered as well towards the middle of the course, essentially. It's to do with like instability. So it's called sliding and overturning. I'll explain that a bit later. We've got fluid statics, so that's basically how does water interact with like buildings and whatever structures you're looking at. And then section properties, which that's more obvious when I explain some more stuff what that is. When we get into the dynamics part of the course, so that starts around week 7, we're going to be talking about essentially kinematics and kinetics of particles, right? So yeah, and I'll explain what particles and rigid bodies and the differences between them are a bit later. And then for rigid bodies, we'll be talking about the concepts of kinematics and kinetics again, just in the context of rigid bodies. All right, so does anyone have any questions about the structure of the course and how it's run? No? Okay. Cool. So a bit of context on this course, right? And I've taught it for a couple of years, and with the civil school and with the mining school before. The way that it's run this year is, you guys are the guinea pig here essentially, because there's a new format. Okay, so formerly there was a final exam. Good news for you guys, there's no final exam anymore, which sounds great, and it is actually quite good news because the lecturer who I've talked to, called Wei, he expects that students will actually do very well this term. Okay, so he's not expecting this to be a terribly hard course, but I also think it's good because it's a very fair course. There's going to be 3 block tests, which is just one way of saying like midterms. So there'll be 3 midterms throughout the term, and they're going to be a very honest assessment of how much you know about the course. So block test 1 will include the content from weeks 1 to 3, and that will be held on Saturday, 10:30 to, I think it goes on for an hour, of week 3. Okay, so weeks 1 to 3 will be covered in week 3. The second block test, which is worth a little bit more, is going to cover the content from week 4 onto week 7. And that will be your kind of big midterm, so that'll be in week 7. And then your final one will be weeks 8 to 10, and that will cover, they'll be run in week 10. So those are midterms, and then there's also something completely new. Wei just wrote this, and he briefed all the demonstrators, including myself, on it recently. And it's the mini project or report. So you basically have like a 20-page document that you've got to write, or up to 20 pages, which sounds really hard, but you basically, like, a lot of those pages will just be screenshots of your calculations, right? So you get to choose between 4 different structures that you'll analyze by hand and with the assistance of like a program like Space Gas. And you'll be consulting with your demonstrators on how to complete that project. So you'll be guided, but it's pretty cool because it's very applied. It's a very applied report. Like what you'll be doing in that report feeds into maybe what you'd do in real life as a structural engineer. So I think it's a really good change. Anyway, do you guys have any questions about assessments, how's it run, or anything like that? No? All right, fantastic. That one's due at the end of the course, so that'll be in week 11, and then no finals, so that's all good. Okay, so Isaac Newton's laws of motion, there's 3. They're really long if you read them. I don't even, I can't recall them off the top of my head, but like I break them down into things that I do know. Oh, thank you. Okay, so the first law is the law of statics, essentially. So that's just saying that when you sum forces, they can be equal to 0. So we'll be talking about this and breaking this down a lot in this workshop. But you can think of this as the law of equilibrium. This is in the context of statics, or you can think of it in terms of inertia. So inertia would be more like in the context of dynamics, okay? So what do I mean by that? So if you've got multiple forces like this, right? Essentially we're saying that, so if you think of Newton's second law and the proportionality of the forces equal to mass times acceleration, it's like if you have all these forces and you add them together, if they're equal to 0, you're in equilibrium. That's what we say, right? And so for statics, when things aren't moving, right? So let's just say statics. Let's say when statics is when your velocity is 0, right? So we've got like this table or something, you know what I mean? Like it's not moving. That would be, this table's in equilibrium, right? So its weight is being pushed up by the concrete slab that we're standing on, okay? In terms of inertia, right? So say you've got a car or something and it's moving, but it's got a constant velocity, right? Its acceleration is 0, but its velocity is not necessarily 0, okay? That is still in equilibrium. It's not, bad word. I like to consider equilibrium when it's not moving at all, so when velocity is 0. Anyway, so basically there's no acceleration, and you can still use this basically equation to describe that. You would describe that more as like, that's where it's sometimes called like the law of inertia, basically. For the law of dynamics, which is the second one, this is the proportionality, saying that a force is equal to the mass times acceleration. So basically you've got the force, which is a vector, you've got acceleration, which is a vector, and you've got a mass, which is a scalar. So if we rearrange this for mass, it gives you like a good description of essentially what mass actually is. So when we think of mass, like for example, if you think about how heavy you are, right, we like to think of it in terms of weight. So that's like vertically. Mass is a scale of, is like a measure of how heavy something is, right? But if we think of like trucks, for example, we've got a big truck, and you've got like a small car or something, right? So obviously the truck's got more mass than the car. If you think of these cars and trucks like moving and then they hit the brakes, the truck takes longer to slow down. So it's got more inertia, right? So really, mass is actually a measure of resistance to force, right? So it's a measure of how much inertia that it has, right? Yeah. So anyway, you'll be using this in the second half of the course to do all your like dynamics questions. And the third is law of action and reaction. So if I push against this desk, it's pushing back at me using a reaction, is what it's called. So you can describe this part. as like an action, and then an equal and opposite reactions going the other way. In the context of buildings and supports and things like that, the reactions are the supports. So you'll see shortly there'll be like a structure. Let's say you've got a beam or something like that. You've got some force on this beam. So say you've got this point load on this beam, and it has to make its way into the ground. You've got two supports, right? Those are the reactions, right? So these supports are essentially, these supports are reacting on the force, and it's keeping the system in equilibrium. Does that make sense? Sorry, I think that was a bit more abstract than I was hoping to go. But yeah. Actually, quick question. Have you guys done physics or engineering mechanics in high school? Put your hand up if you've done physics. Put your hand up if you did engineering studies, I think is what it's called. Okay. Sorry, I probably should have asked at the start. I'll try to like tailor my explanations, okay? Okay, so I've got a bunch of things to explain, okay? Does anyone have any questions about what I just said? I realize it wasn't the clearest explanation that I could have done, but yeah. Okay, that's Newton's laws of motion. It gets less abstract after that, okay? So the first one I'm talking about is equilibrium, okay? So, okay, let's say you've got a ball on a table, right? So think of like a pool table ball, right? And you've got different forces pulling it in different directions, okay? So let's call it F1, F2, F3. We can do the sum of the forces is equal to 0 in the x direction, and the sum of the forces is equal to y in the y direction. And we can actually so say we've got like 2 out of the 3 of these forces. We can work out the third one just based on this concept of equilibrium, where it's all the forces are supposed to be balanced out, okay? That's something called particle equilibrium. All right. So that's the first thing you kind of got to understand. And actually, as a matter of fact, I'm going to show you a little game so the game goes like this. All right. So you got all these team members, and you're trying to pull the string tight and move it around. And I just want you to recreate these drawings. This one we're going to do. First drawing, I'll give you 1 minute to draw it. Draw this, please. Time's up. All right, you ready? We're going to go on to the next picture, all right? You got 1 minute. 2, 1. All right, next one. Last one. All right. And then 1D, 2D, and 3D, okay? So essentially, rigid bodies is how we treat objects, right? So okay. Have you guys used Blender or like you played like 3D games or anything before where you've got like objects? So in Blender, if you've ever used it, or like Unity, if you've ever tried to make a game, right? There's this idea of a rigid body. A rigid body is a body that doesn't deform. So it can't be squashed or stretched. So there's a rigid body and there's a flexible body. So flexible bodies are more complicated because they're flexible, they're squishy, they can warp and deform. And the way that we learn it in not only this course, but it's an assumption that you'll see throughout your whole degree, is that we're dealing with rigid bodies. So the objects that don't deform, essentially, right? And there's different dimensions to them, okay? So the first one is 0-dimensional, right? So if you think of like a single point in space, we call that a particle, right? So if you're in 0-dimensional, if you're operating in 0 dimensions, you have a particle. Okay, so that's just called a particle. If you have a 1D, if you're operating in 1 dimensions, I'm not doing that as a dot point. That's just like a dot. You have a line, right? So a line is called a 1D rigid body. Okay, and where you see this is a beam, a column, anything that's linear. Okay, so anything that's a straight line is a 1-dimensional rigid body. Okay, and 2 dimensions would be like a sheet of paper or something like that, right? So 2D that's a bad example because it's flexible, right? But a 2D rigid body is how you would design like a wall or a slab, like the thing that we're standing on right now. That's a 2D rigid body. And of course, you've got a 3D rigid body, which is like, as you imagine, it could be any shape that's, you know, in 3 dimensions essentially, right? So that's the most complicated one. And I believe in this course, you'll definitely encounter particles. You definitely encounter 1D rigid bodies, and maybe in the dynamics portion, you might run into 2D rigid bodies as well. Okay, so does that make sense? Yeah? But we don't really do 3 dimensions because it's hard to like do on pen and paper, right? But essentially, like this whole building, how it's mapped out from a like structural engineering point of view is it's 3-dimensional, right? You've got members like going that way, this way, up, down, etc. So yeah, in reality, a lot of like buildings and things we do is 3-dimensional. Okay, does anyone have any questions about rigid bodies? So again, it's like I'm trying to teach you things that they'll never explicitly say, I think, in the lectures or anything. It's just like assumed knowledge, and it's always assumed knowledge, right? So I'm trying to point out these systems that are in this course, that's embedded into the course deeply, and so that when you do see it, you know what you're looking at. Do you know what I'm saying? All right, the next thing is moment equilibrium. So let's say, for example, you've got a nut and like a wrench or something like this, okay? And the axis of the nut is basically into the page, like you can see. And if you're applying a force, let's say there, you've got something called a lever arm, which is the distance from the force to where that point of rotation is, right? This is called a torsional torque, I guess. So this is a force, and the whole thing generates something called a torque, right? And I guess more deeply than that, and you'll learn this in the second week, is moments can be broken up into bending moments, which you'll see when we do beams, right? And torsional moments, okay? Yeah, etc. Moments. But another way to say torsional moment is torque, okay? Anyway, so if something's in moment equilibrium, it's basically we're applying torque in that way, and then let's just say there was another wrench behind this one that can somehow fit on this nut, and it's going the other way. Now it's balanced out, right? So now that's in moment equilibrium, essentially. Yeah. Sorry, I'm covering up what you probably need to write down, but that's the way it works. So a question you might have at this stage is, what's the difference between a torsional moment and a bending moment, right? Here's where I'm just kind of yapping, and I'm just going to find myself some space. Give me 1 second. So if you've ever seen a beam, so imagine a plank of wood that's like bridging a gap or something, like, you know, and it's suspended in the air. You might be able to model that piece of wood like this, and you've got 2 supports on either side. Let's just say it looks like that. Oops. If we have a force like that in the middle of the beam, it causes the whole thing to bend like this. So this would be the deformed shape. And then basically, you can think of it like generating bending moments, right? So bending moments and torsional moments, they look like this and this, but what exactly differentiates them? It's how it's going about the axis, okay? So think of it like there's an imaginary dashed line that runs into the page. Actually, I might draw that in 3D so it's a bit clearer, right? So if you've got that nut, the axis of the nut is like this, right? In and out of the page, right? And if you're twisting around that axis like that, you're generating a torsional moment or a torque, right? But the axis of the beam, again, it's easier if I draw it in 3D. The axis of the beam actually runs through the beam. So before I mentioned that we can consider a beam as a one-dimensional shape, right? So it's like linear, right? So it's a 1D rigid body. The axis is this imaginary line that runs through the beam. And so when we apply something, if we have like a bending this way relative to the axis, right? That's called a bending moment, essentially, right? So yeah, anyway, you can probably see quite visually here how a bending moment would be different to a torsional moment or a torque. Okay, any questions about that? Okay, so that's bending in this moment equilibrium as well. Okay, so just talking about beams for a second, right? So again, let's use that example of a plank of wood, and you've got the supports and all that. All right, and we've got something called a uniformly distributed load, right? So that's basically like a load or a force or a weight or whatever, and it's distributed, right? So if you think of a dude and he jumps straight into, let's just say, quicksand, okay? You can think of that like a point moment. So his force would be concentrated in, let's just say, one spot, right? So that would be a point moment. Oh, sorry, point load, I should say. Let's call it a point load. But if that dude jumped onto the quicksand and he had a surfboard, and let's say this surfboard's perfectly rigid, the force is transferred from him into the surfboard and then distributed and spread out across the quicksand, right? And so that's what a distributed load is, essentially, right? So it's where you have a certain length or area that you're distributing your force over, and that's a distributed load. So if we think of it like this beam, right, has length of L, and you've got the force, but now we've got the force over the whole beam length L. We usually notate it with lowercase w, so that's a distributed load. And the units would be, so if the force was in kilonewtons, right, the distributed load in one dimension, so one dimension along the beam, is in kilonewtons per meter. Okay, so we've got a linear distributed load. Anyway, so we've got this whole thing going on, and essentially, we can slice the beam at a certain point and think about its internal forces, right? So taking into consideration like the idea of equilibrium, right? So before I showed you guys equilibrium being like strings being pulled in different directions, those are all external forces being balanced out. Okay, so I'm going to use the word external. So those are external forces being balanced out, but if you think about the object itself, which is in this case a beam, like a 1D rigid body, it also has internal forces. And if you have equilibrium, you've got this object and it's got external forces being applied on it, which is in this case is the distributed load. And then in itself, it's generating internal forces to balance that out so that it doesn't move, okay? That's where you get this concept of beam internal forces from. And that's the stresses inside the beam trying to react to the external forces, okay? Does that kind of make sense? There's a lot of concepts I'm just pulling out of thin air, but you just gotta trust me for now. Okay, I'll explain them a bit more as we go. Okay. So if we want to slice this beam in half, we can basically, so the idea of like a free body diagram or like a section is, we're currently analyzing this part. This is like the section that we're looking at. We're not analyzing like the sun and the moon and the bloody like, Jupiter or something like that. We're just focused on this, and this system is in equilibrium. But if we were to capture just a part of that, we need to expose the internal forces in the beam so that the system's still in balance, so the system's still in equilibrium, right? So I'll show you what that looks like. So we've got this beam. We're going to cut it like this, okay? And I'm still going to draw the part of the distributed load, W, like that. But now we have internal forces inside the beam that will be exposed. There'll be N, which is your axial force. And since, okay, no, too much, sorry. Okay, this is V, which is the shear force. And this is M, which is the bending moment. So basically the ones which will be non-zero in our case will be the moment and the shear. So this is called internal moment of the beam. And this will be called internal shear. Okay, so you'll learn about this more in week 4. So this is week 4's content. So basically, sorry, I'm jumping all over the place. Where I'm going with this is, I've told you about forces, the force equilibrium, that was the little game we played. That's week 1, okay? Week 2 is moments. So talking about the torsional moments and the bending moments a second ago, that's week 2. This concept of internal forces and how a beam like behaves and stuff like that, that's week 4. It's week 3. It's week 3. sorry, it's week 3. Okay? So this will be in your first block test, yeah? Okay? So if you have any questions, it's great to ask it now, because this will be in your first block test, which will be coming up. I know it's hard to like fully comprehend without having done like some practice problems, But yeah. Anyway, feel free to ask me at any point. So the next thing I'm going to tell you about is trusses, which is week 4. Okay? I can see some people still writing. I'll share the notes with you guys definitely after this, but I'm just going to scroll down, all right? Is that all right? Yeah, sorry. Or you can take a picture or something if you want, but yeah. Okay. Okay, so trusses, right? Okay, so trusses, basically you might have seen these structures before, but let's just start with a very simple one. So we've got the supports, right, which would be like down here or something, and you see this triangulated shape, and let's just say there's a point load here. Okay, so basically the question is, what makes a truss a truss? So you might have seen trusses before, like bridges or maybe cranes or girders or something, and you just see they're like a series of triangles. Okay. The question is, what makes this different to a beam? Or what makes this different to a column or whatever, right? And there's a few things. The first one is that they only receive something called axial forces, right? So axial forces, when I'm talking about axial forces, I'm talking about tension and compression. Okay? And unlike a beam, they don't receive shear and they don't receive moment, bending moment specifically. Okay? So they don't receive these ones. Okay? So how do you set up your truss in a way? Okay, wait, firstly, one thing I haven't said, sorry, is that a truss can't be a single member. Like a beam can be a single member, it can be a straight line. A column can be a single member, like a straight line, but up, A truss can't be, because a truss is a series of members that behave together to achieve the goal of carrying only axial forces, okay? So when I show you a simple truss, minimum it has to be a triangle with 3 members, okay? Minimum. All right, so how do you set up your truss system so that it doesn't receive any shear and bending, okay? So basically, let's start with shear. So shear is basically, if you've got a member like this, right? Let's just say it's floating in space. Tension looks like this, where it's being pulled apart. Compression looks like this, where it's being pushed together, right? So what does shear look like? Shear looks like this, or like this, where you've got, okay, I'll jump to the conclusion. Basically, if you have a transverse force being applied in the middle of your member, it's taking shear. So what do I mean by transverse force? I mean it's happening perpendicular to your member. So I'll give you an example of where you will have induced shear. If I did that to the truss, it's now experiencing shear. Okay? So you'll see this more in depth as you do your practice problems like week 3, week 4. But if I ever have a truss where there's a force being applied halfway through, right? So imagine I've got like a ruler, just pretend I've got a ruler on me, and I've applied this force, or like my finger pushing, onto the ruler halfway. It's going to be taking shear and bending now. It's not taking axial only, right? Does that make sense? Kind of? Okay, all right. So that's one thing about trusses, okay? They have to take all of their force at the ends, okay? That's how you induce tension and compression. So it can be here through a reaction, and it can be here, for example. It can be horizontal, whatever. As long as it's at the end of the members, you're only inducing axial tension and compression, okay? The other thing is that these members will have pin connections. For example, my elbow is pinned, right? If I do this, it's pinned. It's free to rotate about my joint here, okay? But something that's rigid, rigidly connected. Imagine if I've got like a cast on my arm or something like that. That's rigid. It can't freely rotate anymore, okay? So these trusses, the idea is that they're supposed to be able to have free rotation at each of these joints, okay? So that's what makes a truss, okay? Most importantly, though, it's the axial forces aren't applied halfway through the member. Do you guys have any questions so far? I know this is like a lot of information overload, but yeah. Okay, if not, I'm going to keep going. So the idea of strength, stress, and cross-sectional area It will be in your assignment, but I don't know if it's actually taught in the lecture slides, because it's more of a mechanics of solids concept, which comes in second year, first time. But it's super important. It's basically this idea of how does a structure fail? Okay, so basically, if you've got a load of some sort, so a load would be, for example, I'm standing on a concrete slab right now. We're all loading it because we're external forces like onto the slab. It has to be less than the capacity of the slab. So the slab itself is strong because it's made of concrete and has steel inside or whatever. So essentially the idea is that you have to make sure the capacity is bigger, quantify it somehow, than the load that we're exerting onto it, right? So if we're taking a step back from the idea of a slab, which is more complicated, and we have this idea of, like, let's say a straw, which this will tie into the next game that I'll give you guys, right? If you've got a straw and you're pulling it, right, in tension, right? So you're pulling it, it's in tension. It's going to basically experience some level of stress, and basically you've got the force, and if you divide it by the cross-sectional area, so the straw is like hollow, right? So let's just say whatever area that hollow circle is the area, right? That makes it sound like it's 0. But yeah, that would be like whatever area that is, and the force would be whatever pulling force we've got going on here. Essentially, this is the whole idea of stress, okay? And yeah, and so if you've got too much stress, your thing's gonna break. So how do you increase its capacity, right? And like you're keeping your load constant or whatever. You can add more straws, right? You add more straws, you've got more cross-sectional area, it's got more strength, it's got more capacity, right? And you can bundle these straws if you want, and you got like 3 and then et cetera, okay? Does that make sense? Yeah? Okay. Look, we'll give you guys a break. Do you guys need to go at any certain time or whatever? This whole thing finishes at 2, but I've got a bridge building activity, okay? But does anyone need to go like before 2? Anything like that? Oh, a few of you? Okay. Whoopsie daisy. You got class at 2? Is that the lecture? We'll try to finish way before then, but yeah. Is that all right? I want to make you guys build a truss. I won't take too long with that, but yeah. Do you guys want to like stretch your legs and all that first? Get some water. 5 to 10 minutes. Oh, I should mention there's a prize, by the way. That'd probably be more motivating. So I've got a lot of printouts of the notes for this course. So you can find these online on my little website and stuff. But it's the whole course, like a textbook, if you will, printed out. And I've got copies for every member on your team if you win. All right, so. Is this the Bible? Yeah, this is the ENGG1300 Bible. So, yeah, this is a really good resource to learn from. So hopefully you can be a part of this. Let me explain to you how it works.
We're going to next explanation pretty soon.
Okay. All right. We're going to change this to 350, and we'll just do 1 tote bag. Let me just delete that. All right. This will be weighed from the middle, like that. Okay. All right. All right. So the way it works is we're gonna build a bridge, and it'll be tested across that gap over there at the back, between the tables, right? And we're gonna score it based on strength to weight ratio. So I've got a little scale. If you overbuild, it should be worth the extra material, if that makes sense. So if you want to slap on extra weight, it's got to carry more weight as well. Okay. So it's based on strength to weight ratio. Whoever wins. I put 1 hour, but I just put a random number. We'll just go, let's say 30 minutes for now, and we'll add on like 10 or 15 minutes if you need it. Depends how quickly we go. We've got supplies that are given to you. And the tote bag will be loaded in the middle. until failure. So it's basically what you can see here. The bridge, I'll slap this tote bag over, and we're gonna chuck weight onto into the tote bag, and so it weighs down your structure. It's like looped around your bridge. Okay. And that's gonna be 35 centimeters, or 350 mil, and you'll get these textbooks. I'll just leave this on the table if you want to load this up until failure, and then we'll measure how heavy the bag is.
Yeah. Alright, which bridge are we doing first?
Maybe we'll do this one first.
Okay.
We should preload it or something.
Whose bridge do you think is gonna win?
Which one's wrong?
I'm not
Okay.
telling you yet.
Hey, you want seconds?
I'm gonna
Why is it supposed to win a bridge, right? Do you remember who I am?
Hey, he's holding.
You do? Farhan.
Class.
Where's Nick?
He's on the way to uni right now. We've got class at 3.
Ooh. Wait.
See that bending? There's a bit of bending there.
Bending moment.
Looks good.
Oh shit, bro.
Oh.
No.
Not yet. Not yet.
Get it back in. Wow.
Ooh. Hold on.
This is looking strong.
Please break.
No.
Keep going.
Keep going.
Please break for my sake.
Oh wow.
You can use my bottle. Do you reckon?
I don't know. Might be a bit too heavy.
Ooh.
Put the shit in my
No, that's good.
That's good.
Ooh.
Okay. Sit down. Yeah.
Oh wow.
Oh, hold on.
It's swing.
Shit. I don't think these tennis balls are heavy.
Do you have anything heavier?
Not bad.
Yo.
Oh my.
Hey, yo.
That's the maximum.
It'd be pretty accurate because these balls are so light. Brother. It's not heavy.
Oh my god. Oh. Oh.
Whoa.
Oh, that.
Why'd you push it?
Brother.
This one under the table.
Yeah.
This one under the table.
Oh.
It's still working. Still counts. I'm out of balls.
Wait, it's Loki slipping. It's Loki slipping. Hold on.
Wait, it's not right now.
Yeah.
GG.
Alright.
That's broken.
Yeah.
Alright, well, let's weigh how heavy this is.
This is the
It's
number
not
of
too
balls.
Hey, that was good. That's not bad.
If it falls before that, the number of balls than us, they lose like, or do we win?
Yeah, I mean, we're gonna weigh how heavy it is.
Oh, then it becomes a skill thing. I hope we can handle all that.
I'm 84.1 for him.
84.1.
Yep. And this is 87 point. Wait, I'm gonna stop moving. Tell me when it stops. Oh,
87.2.
87.2.
So 3.1.
Which bridge?
That's bridge
This is the
2.
heavier one.
Yeah. 87. 87.
Alright, congrats.
Why did
So
it sound like
3.1 kilos. Whoops.
we can do that.
Not bad.
You know that we can do that, guys. Believe in our game.
Yeah. Let's put some heavy stuff at the bottom so that these balls will. Like, we'll do the first.
I figured out the single triangles on the strat. Look how flimsy it is.
Yeah.
Anyway.
Let's concentrate the stress on the middle. It's this. It's this.
It's looking sturdy.
I'm stressing that.
We can get his water bottle over there. There's a water
Got
bottle.
more water bottles?
Can we use that one? Whose
Yeah,
is
get
that?
another one.
Yeah. Get Ryan's bottle. Yeah.
Let's get multiple water bottles.
Let's get multiple. Yeah. Let's get multiple.
Yeah.
Yeah.
This one's kind of heavy. Wait. Oh shit, this one's kind of heavy.
We got it, we got it. Hey!
Ooh, hold on.
Yeah,
It's kinda tilting.
No. It works. Go. Yeah, tennis ball.
Wait, the tennis balls now.
You got? Is my lid closed?
Yeah, these are close. It's kind of twisting.
Yeah.
I'm just gonna let it.
Oh come on.
Making
Come
some
on.
No. There's more.
Let's
No, no, it can go more. Whoa, wait, let's see if you can
More? What do you mean?
Guys, it can go more, it can go more, bro. What do you mean? Have a second.
No, you can see how it's going down, bro.
Should I keep going? No.
It's about to. Yeah.
That's it.
Yeah.
Alright, that's each. Alright.
Does that feel heavier?
Me plus the water bottle. Oh, 87.4. Check the strength to weight. Strength to weight. It doesn't matter what units as long as the numbers.
That one weighed less but carried more.
Really?
Yeah.
Wait, which one?
The second one.
3.3
The second one we just.
Well, weighed less but carried more.
3.3 divided by
Oh, by 0.2.
times.
Just by 0.2.
They carry 47 times their own body weight. 47.8 tons. Is that right? I did this divided by this.
So the very first one we tested was
40 times its own body weight. Does that make
Oh
sense?
wait. Like the first one we tested. Oh right, but the one we just tested now.
Yeah, this
One.
is the one that we just tested.
All right,
yeah.
you guys win.
Alright, congratulations.
Nice one, guys. Nice one.
That was a pretty good effort, actually.
Alright, good job, guys.
I
Alright.
think